Do you need extra help with your elementary Chinese 1? Yes, I do. I could be. Learning foreign language is impossible for me. It's one of the questions that, sometimes people get if you help anybody like with an algebra. Like normally think of college algebra or elementary algebra. Like when do you use algebra? In a strict sense, for the idea of an algebra is the idea of find the unknown. And if you would think about it that way, when you use algebra, you have things that you model, find the unknown. We do this on a daily basis. Whether the unknown's a function, a rule, a number, a proposition. When you have discussions with people and you're trying to figure out, decision making of any sort, that fundamental algorithmic process is in algebra where you have objects and you say, okay, what's this? What am I going to do? Find a function that represents something. When are you going to cross an intersection? Timing things out. Those are all about the idea of modeling and trying to break it down and finding unknowns. One of the more interesting things about like the whole axiomatic method and proofs, when do we use things like this? And I think the idea of building up under assumptions and then trying to build a system upon it, what's the oath that doctors and nurses take usually? What's a doctor take? Which is what, essentially?
Do no harm.
Right, and so you build out a system from that. You have things that I am going to have this as my fundamental, and from there I'm going to build up, for them, a moral structure above it. And you guys do the same thing whether or not you take your oath. If you're going to go on to computer science, and you become a system administrator, or you're a person who's actually helping somebody with their computer of any sort, do you have a built-in axiom in your head that may or may not be worded, which is, I have an awful lot of authority and power. I'm going to try to be moral to this person. I'm not going to go and help them and download every picture off of their thing. I'm not going to put things on it. When you design stuff, we have, outside of what we expect, like, well, I'm doing proofs. One of the things that we're doing with this idea of fundamental things that we build on top of, we do it anyways. What's more interesting to me at times is, do you guys think about that? When you take your moral, coding and programming morality, what about morals in business? What about morals in your daily thing? We have fundamental things that you're going to have to build that structure on. Now, most of us try to get along without thinking about it, but it's good to say, what are my axioms? What am I building on? But these are things that we go through it and say, all right, from here, this is going to be my basic understanding. From that basic understanding, let's move and build on. And we have to, at times, tear things apart. So anyways, we're going to be tearing things apart strictly here, usually doing an awful lot of just straightforward integer work for most of this, and we'll build on the number theory after this. But for now, as we're going through this, I think chapter 4 is when we hit number theory. We still have the idea of what's my assumptions and what do I build and how can I create new things. So questions before we get into lots of proofs. All right. So eventually we're going to get to answer this problem today, which is prove square root of 2 is irrational. Again, prove means give me a valid argument. Give me a valid argument that it's true that square root of 2 is irrational. There's some certain things that we're going to have to do this, and we're going to be talking about techniques to get to this point. Again, this is an example in your text. This is a one that we're going to do here in class. This is also going to show up on your first exam. And it used to be about a large portion, I'd have to actually do statistics, but 60% of statistics are made up on the spot. We just make up a number and say a lot. But if I say a number, somehow it makes it sound better. Right? Yeah, and that's that whole. It's like you go through it. It's like a good example is you'll read those. They asked the one guy about they were going to change rules for hydrogenated oils. Right? You bubble hydrogen through an oil, makes it more like all the way up from an oil to a wax. things like Oreo cookies. It's like, oh, these are dangerous, so we're going to get rid of them. And they ask the person, they're coming up with this new rules to get rid of them. And it's like, well, how many people will it save? Well, I don't know, but it'll surely be in, and he gives a number. It's like, don't do that, right? But we do, right? When we have arguments, it's not a valid argument. It's actually a fallacy, right? It's one of those things where appeal to authority. I know what I'm talking about, but you just told me you didn't. So be careful when you have those arguments. And so when we're going through these things and saying, all right, what does the word irrational mean? What does this symbol here mean? If we're going to go through these arguments and try to get them down, all right, you're going to have to work through this, but I said it, I will show it. It's on the first exam. A lot of students left it blank on the first exam. Even though I said it on day one, I showed it in class, I said it's an example in the book, and I will demonstrate how to do it. A big portion of the students used to leave it blank. I got that number smaller by saying the following. If you leave this blank on the first exam, you need to think long and hard if you should even be at a university. If you're not willing to put in the effort from today to the first exam to at least put down the fundamentals of this proof, to say, I don't care enough to even do anything in the next week before this exam, I'll just leave it blank. I don't think you necessarily have, say, I don't care. It's $3,000 I throw away per class. It doesn't matter to me, right? You have to be serious about certain things. And me being this obvious, you should be able to do this problem. Does that make sense? Okay, being at a university requires certain levels of emphasis, and that's one of them. I consider fundamental. Caring at all. Now, saying that actually lowers it, but there still will be people who leave this blank. All right. Don't let it be you. If you sit in the front row and you leave it blank, then all right. Techniques. Techniques to prove. The first thing we talked about, the idea of one, is if we're going to do things like, if I'm asked to prove and I have some sort of implication going on, right? Prove if this, then this. We have something, or this whenever this. Or just actually, one of the things you could do is alone have the conclusion, because we could have it be enthematic. Well, what's the hypothesis? Well, what do you think it is? So if I say prove square root of 2 is irrational, what do we have to know? What's irrational? What's square root of 2? Those all go into the implication. You have to assume those sorts of things as we go into it. You just have the conclusion. So normally we have the direct. A direct proof like we did last time, we could do things like, how about this? If n is even, then n squared is even. What's a direct proof? A direct proof is assume the left and then show that the right logically follows. If the left is true and the right is true, then we've shown that the second line of implication doesn't happen. The right must be true, so true implies false is impossible. So we would do things like, okay, here's my proof. I'll just simply assume that n is equal to 2 times k, where k is an integer of some sort. We usually use k for integers, or I or L, one of those sort of letters. Is that an even number? All even numbers are 2 times something, but it has to be an integer. What's 2 times pi? Is that an even number? No. It's 2 times an int is what an even number is. All right, if that's true, all right, what do I know about equalities? What I know about equalities is what I do to the left-hand side, I can do to the right-hand side. So if I multiply the left-hand side by n, I can multiply the right-hand side by n, but n is also 2k. So that's the same thing as saying that I could have a multiplication of both sides by themselves, right? Because they're equal, just squaring it. We also have the ability to apply functions to both sides of an equation as long as functions meet continuity rules. All right, but if n squared is equal to 2k squared, what is 2k squared? If I were to go ahead and multiply it out, So it is 4k squared. Now what's my goal? To show that it's even. All right? When you're doing proofs, you need to know where you're at and where you're going. Sometimes when you do the work, you would take where you're going and ask, what would happen before that? What would happen before that? That's called a backwards reasoning. Start at the answer and say, you're not going to prove it that way, but say, if I'm going to get to Salina, I'm going to first have the city that I would go through probably right before Salina would be Lynchburg, and then before that would be McPherson, and before that would be Heston, and then before that would be Newton, okay, and then Wichita. Now what do? Okay, Wichita to Newton. I would know which cities to go through, right? One, going from where you want to go back to here is backwards, forwards is just go. Not everybody can see forwards. Sometimes you want to think both directions and figure out where they meet, right? So if I asked to say things like, if I had my father-in-law helped set up a plant in China for AGCO, and one of the things that asked was, well, if he was going to get to a particular place to test out a tractor in Inner Mongolia, Mark, go there. I have no idea how, but what could I do? He could do the backwards part, right? How do I get to that? I just want to get to you, and then you take me the rest of the way, right? And that's how we do a lot of proofs, right? You kind of join in the middle somewhere. But on the other hand, I want to show that this is even. But what does it mean to be even? 2 times a int. That is what it means to be even. Do I have 2 times an int? Is that an integer? What's k? What's 2 times 2 is an int. So int times an int times an int. Integer, right? That's a property of the integers. And so this happens to be that's an integer. And so the answer is, yeah, that's true. Physically, what is this saying? Well, the word square means square, right? This is, if you have a square and the length of the sides of the square is even, the area inside of the square is even as well. All right, sometimes this doesn't work. What if a person asks, well, what about the other way? It's kind of interesting that if I have a square, and that's an even-sided square, that it ends up being even area, right? That's what I just showed. If it's an even side, it's an even area. Well, what if a person asks, does it go the other way? What if they say, could you prove that if you have an even area, it had to have been an even side? Another technique we can use is the contrapositive. All right, what's the point? All right, if I tried to prove this directly, what would I assume? If I try direct, I would assume that n squared is equal to 2 times an integer. Let's use I this time, where I is an integer. And I'm going to do some work, and what do I need to have? N is equal to twice an integer. Can you think of any algebra based upon equalities that would get n by itself so that I had a 2? People say, well, how about take the square root of both sides? Are you allowed to do that? What if I is a negative integer? Can you think of any algebraic work where I could go, I have an n times an n, this is what we have. A number times a number is twice an integer. Could you do something in algebra so that I get n by itself and it ends up being twice something? Can you think of anything in algebra, all the laws, the things that you're allowed to do to equalities that would allow this to happen? And the answer is no. None of them will do that. There is nothing I can do in algebra so that I have an n times n and end up with an n that will work out the way I want it. We kind of scratch our head on that and say, all right, fine. I can't prove it directly. This can't happen. So no algebra can do this. So am I stuck? So we go through this and say, all right, this didn't work. But what do I know? Left implies the right is logically the same as what? Not the right implies not the left. That's the contrapositive. So what do? I can't show the left. It's too hard to do. All right, fine. Let's write it a different way. It's the same thing. It's a different look, right? So what does that mean? Well, for this problem was n squared even implies n even. Right? Would be logically what? What's not n is even? N is odd. Now, what if this worked because numbers are either even or odd? What if there were three classifications, like I talked about remainders? If I divide by 3, it has a remainder of 0, a remainder of 1, or a remainder of 2. If it's a remainder of 0, it's called divisible by 3. What if I said it's not divisible by 3? You wouldn't have a one option. If it's 3 possibilities and you say it's not one of them, it's what? One of the other 2. I have 2 cases to deal with. Right, but this one, there's only 2 cases. It's even or odd. Well, it's not even. Oh, odd. That's my only other option. What if I had 5 cases and I said it's one of these 5, and it says, well, wait, it's not the 5th. Then you would have to test how many? 4 cases. So for this example, it's just simply n is odd implies n squared odd. But that's only for this. I mean, when we work out problems, what is not something is sometimes a little bit more difficult than this. All right, so instead of proving this, prove this. So the first one was too hard to do, so let's try that one. Well, did we do that last class? Can you prove that directly? Prove n odd implies n squared is odd. All right, what do I assume? I'm going to try direct, which is n is equal to 2 times I plus 1, where I is an integer. And therefore n squared is equal to 2i plus 1 squared, which is simply 4i squared. I wrote a t for some reason. 4i squared plus 4i plus 1, which happens to be twice 2i squared plus 2i plus 1. That happens to be a integer. So yes, it's true. And because this is true, since true is n odd implies n squared odd, and that's logically the same as n squared even implies n even. That's a proof by contraposition. I proved the contrapositive. So the original didn't work for me, right? The original one was too hard, so let's rewrite it. It's logically the same. It ends up with that a new look at it of the same problem is one I can approach. So that's a common technique that we use. Just look at it just a little differently. If this side doesn't work, okay, let's look at it from the right. All right, we're good. Try that approach. So what do I know? Well, actually we have another example here. These two together, these two problems, today we actually showed that n even implies n squared even, and n squared even implies n even. What is that the same as? What logical operator? If left implies the right and right implies the left, what actually we have done is we actually have showed n even if and only if n squared even. We'll talk about that here in a little bit. And so what does that tell us? Even-sided squares have even areas have even-sided squares, and that's it. What if it's an odd side? Well, it's going to be an odd area. What if it's an odd area? It's an odd side. It's an if and only if. All right. What if we get to, say, one more, and we finally get to this problem? Prove square root of 2 is irrational. All right, the technique we're going to do on this one is called proof by contradiction, and what we're going to do is if you want proposition is supposed to be true, right? The thing that I proposed, my conjecture, if I put it that way, if I want my conjecture to be true, but it is too hard to do. You tried a direct proof, you took its contrapositive, you tried that, still doesn't work, you don't know how to work it out, we're kind of stuck a little bit. We could just simply say that, okay, fine. How about let's rather try not the proposition, is logically not true, which is what? False. Normally proofs are use a valid argument to show that something is always true. Well, what do I want now? I want a valid argument that shows something is always false. Well, if it's always false, its negation must have been what? True. Well, why would I want to go to, this is why it's called a proof by contradiction, because what is always false? What's another word for always false? Contradiction, right? Always true is tautology, always false is contradiction. So we shift it. Why are we interested in contradictions? Because under the word and, who dominates? False. So if I can somehow get this problem with an and I end up with a false, then the entire thing falls apart, it's false. Because false is a dominator of conjunction. So that's kind of our goal. And so doing this technique of showing something is always false, then its opposite must have been true. This is called a proof by contradiction. Sometimes I would replace that word with an of, right? It's proof of a contradiction, right? I've showed something is always false. That was my whole point. Therefore, its opposite must have been always true. But technique-wise, it's called proof by contradiction. And we're going to do that for this. Why do we normally use contradictions in particular problems? All right. Irrational. What's the ir mean? Not. All right, so you're wanting to show something is not rational. All right, that's usually hard. To show something is not something. Show Mark is not human. All right, that means of all possible humanness, he's not that. That's difficult to work with. But if I would negate it, what would I assume? What's not? Is. It's easier to work with an is. If I said a number is rational, all the properties of rationals can now be applied to this. To show something is not rational is usually, directly is difficult. Because not things are hard. Things that are, you at least have something to work with. So how does contradiction work? Well, let's try an example of one we already did. So let's try prove n squared is even implies n is even. All right, it's too hard to do. But I'm going to note something. What happens when I negate what I'm talking about for this implication? What is not left implies the right? Anybody remember that? What is that logically the same as? It was not, it's left and not right, but, so let's say not left or right, which is logically left and not right. Everybody okay with that? So what do I have? Something rather useful, conjunction. So not that, so I'm going to try contradiction. So proof by contradiction. So again, what's your goal? Because it's contradiction, the goal is not the statement that you have needs to be false. That's what I want to do. Not this is false. But what did I just show? What is not the statement? I have the left and I don't have the right. Well, what's the left? N squared is even. And what's not the right? N is odd. Is everybody okay with that? All right. What does it mean for n squared to be even? What's the definition of that? N squared is equal to twice an integer. I is an integer. And what does it mean for n to be odd? N is equal to twice an integer plus 1. I've already used I got to pick some other letter where k is an integer. Everybody okay with that? Both these are supposed to be true. They just are true, right? So the left is n squared is twice an int. The right side is, well, n is actually 2k plus 1. Well, if that's true, n squared is equal to what? Remember that whole 2k plus 1, the quantity squared, which is 4k squared plus 4k plus 1, which is equal to what? Twice 2k squared plus 2k plus 1, right? See above. Well, what is that? That's an integer. What does that tell me? Well, here's my question. Is it possible for n squared to be twice an int at the same time it's twice an int plus 1? Is there any number that is twice an int and the other one is twice an int plus 1? Is that possible? That's like this. Mark is standing and Mark is not standing. What is that? False, right? So what we have is these together, n squared even and n squared odd is logically what? False. We're done. The opposite of what I once wanted is false. Therefore, the original must have been true. Kind of working around, right? I'm dealing with its opposite. Its opposite's always false. Oh, okay, it must have been true. That's the only way for that to happen. Is everybody okay with that? A lot of times we're not used to kind of dealing with, we're so used to dealing with only tautologies, right? I always want true, I always want true, I always want true. Contradictions, things that are always false are just as powerful, and they can actually do some subtle things, right? But we're not used to thinking in, I need to find an always false. I need to show it's always false, but we're used to thinking always true. So it kind of like goes against the grain. But it's a very powerful technique. All right. So if you're going to prove square root of 2 is irrational finally. To prove this, a couple things have to happen first. One, you have to prove if n squared is even, then n is even. And this would be a lemma, because we're going to eventually use this. How is this proved? What techniques were used in this? the contrapositive, and then how did you prove the contrapositive? Direct. So this was proof by contraposition. How? Contrapositive, and then direct. Oh, you had to use two things. I had to be able to flip it as a contrapositive and then use a direct proof. We already did it. Or I could use it like we just did, contradiction, but this is the better way to do it. So it makes more sense. All right, after that is done, the second thing we have to know is, what is an irrational? All right, a irrational, we have to know this, means not rational. Well, rational means this is A over B such that three things happen. One, B is not 0. Dividing by 0 makes no sense. 2, A, B are integers. It's an integer divided by an integer. 3, A, B have no common factors. So the word irrational means it's not that. What are rational numbers? So what are examples of rational numbers? 4/7, integer over integer. Yep, no common factors. That would be good. That is rational. Okay, rational notation-wise is a double bar Q, just so we know. So that would say it is, that is element of that particular set. On the other hand, what about 8/16? Nope, it's not in it. So that is not. So we would take this one and say, no, that's not rational. People say, well, wait a second, isn't that a half? That's the point. If I allow common factors at all, sure. When I would draw this on the number line, it would be 1/2, right? And I would put it at 0.5. But that would, if I would allow common factors, that would mean how many ways could I write a half? If I allow common factors, that means I could write 1/2 is the same thing as 2/4, which is the same thing as 3/6, which is the same thing as pi divided by 2 pi, which is the same thing, all right? Do all of those numbers go to the same point? Yes. How many ways could you write, therefore, that one point? A lot, right? Infinite. So by saying, look, 1. If you say no common factors, there's one way to write it, and that is just this number, and there's no other way to write it. That's the point of doing it this way. That's why one is irrational, the others are not. All right. So that is here. This is enthematic. This is what you should know. When I say rational, that's what I mean. So if you say something's rational, that's what you say. All right. So here comes our proof. I'm going to try by contradiction. So I'm going to assume, right, we have hypothesis, which is all the stuff, rationality, I know what square root 2 means, right? I'm going to assume not the conclusion, right? Which is, it is not true that the square root of 2 is irrational. Again, what is my goal? My goal is that this should be logically what? By the end. False. That's my goal. That was the whole point. Because showing it's logically true is difficult. It's not. They'll show it's logically false. I've done the same thing. All right, what does that actually mean? All right, here, is this valid reasoning? What are things that you can assume? The hypothesis. What else can you assume? You deny the who? Conclusion, that's valid. Assume the hypothesis, deny the conclusion. We're still good, right? We're doing valid reasoning. There's no problems here. What would happen if I assumed the conclusion? That's the fallacy of assuming the conclusion. Under a proof technique, that's usually called circular reasoning. You assumed what you were trying to show. You're not allowed to do that. That's not valid reasoning. You deny what you're trying to show. So we're still good. What does that mean? It means square root of 2 is rational. What does that mean? Square root of 2 is a rational number, which is what? Something divided by something such that b is not 0. They are integers. And a, b have no common factors. So that's what I'm assuming. All right, now what do I have? Well, I have an equality. So what needs to come along? Algebra. Let's do some algebra. I don't like that. I like integers. How can I get rid of that square root? Square both sides, which really means multiply both sides by the same thing. We're allowed to do that. If I square both sides, square root of 2 squared is equal to a over b squared. Allowed to do that. What's the left? 2. What's the right? I don't like fractions. Nobody likes fractions, right? Take 7/11ths and add 15/16ths. Right, I don't want to do that, right? So how could I get rid of the fraction? Are you allowed to? Why? I see people do it like, let's move the b squared to the other side by multiplying by b squared, multiplying by b squared, and that becomes 2b squared is equal to a squared. Why was I allowed to do that? Because 1, it is equal, and I can multiply something on both sides as long as that something is. What's the one thing you cannot multiply by? Which is the multiplicative dominator, right? Because think about it. I can show, if I did that, I can show 1 equals 2. How? 1 times 0 is 2 times 0. 0 is 0, obviously. Right? You can't multiply by the dominator because it just knocks everything apart. Right? That's a bad thing. Right? The rule of algebra is you can multiply both sides by the same number if it's not 0. Right? If you would have left this out, I erased that b can never be 0. If I would have left that b not a 0 out, could I go from here to there? No. Because I don't know if b is 0 or not. I can't move it. But it's not 0. Good, move it. That's why I can do that. Now, how often have you done things not knowing that in the back of your mind? Oh, wait, I can only do this because it's not 0. We move things all the time without thinking hard about why. All right, now let's look at that. What does that tell you a squared is? Well, what's b? An integer. So what's b squared? An integer. So 2b squared is even because who? Whoops, wrong thing. I wanted to, good thing it didn't erase it. B's an int. Because if I wouldn't have written that, I wouldn't be able to say the next thing. A squared's even. I couldn't have said that. All the time people say, well, it's twice. Twice what? 2 pi? That's not even. No. B's an int. Okay, good. It's twice an int, so it's even. That's why I can say it's an even. But what happens? We say even without knowing why we said it. All right, now, by lemma, because a squared is even, that implies a is even by the lemma we already showed, right? It doesn't just immediately follow. That lemma says you got an even area, it must be an even side. And that's already been proved, which is why this must be proved first, because I use it. By lemma star. All right, what does that mean? What does it mean for A to be even? A even is what? A is twice an integer. All right, let's go back to here. So, 2b squared equals a squared. A's that. A's that. Can I replace something with its equal? Yes, I can replace things with their equal. That implies then that 2b squared is actually 2i, which is actually what? A squared. Okay. What's 2i, the quantity squared? 4. That implies that 2b squared is 4i squared. Can I divide both sides by 2? Why? Because 2 is not 0. I'm multiplying by a half. So that implies that b squared is equal to 2i squared. But what's I? An int. I squared is a int. So that, what does that make b squared? B squared is even, and therefore, and by lemma, B is even. All right, now I have these two words here. I had B is even, two statements, sorry, and I had A is even. I have two propositions. B is even and A is even. What's my problem?
They're both divisible by 2.
All right. We have A is even and B is even, which is really what? Common factor of 2. Dun, 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 dun. Let's go all the way back here. What was the third thing that's true? They have no common factors. They literally had no common factors, but they literally have a common factor of 2. Is that possible? No common factors and common factor of 2. That is false. That's my contradiction that puts together. So hence, we have no common factors. Where did that come from? The fact that it's rational. And common factor. It doesn't matter, of 2, but that's logically false. Therefore, square root of 2 is irrational. And we're done. Because what have I done? Square root of 2 is rational is always false. Okay, square root of 2 is irrational. Is always true. Yes?
When we put on the test, you want us to write down everything that is about rational, or when we say it's rational, can we assume that
No.
everything else is rational?
When you say rational, I want you to state, when you say it is rational, I want to see those statements. Now, when you use those statements, like you move the B, I only can do that because B was not 0. You don't have to say it, but you have to know it. When you had that B squared was even because it's twice A squared, right? Sorry, A squared is even because it's twice B squared. That's only even because B is an int. Okay, but you know that because you stated it. And on the other hand, no common factors definitely needs to be stated because that's where the contradiction comes into play. I want to see you state all those 3 things because they get used all 3 times. Now, on the other hand, when you use them, a lot of times it's like, yeah, I know what I just did. Don't try to memorize. This is obviously complicated enough that if you just try to memorize it, it's going to be problematic. I want you to understand why this happened. How would this change if I wanted to show things like the square root of 3 is irrational? That'd be the square root of 3. That'd be the square root of 3. That would be a 3, which would then make this a 3. And so what would that tell you? That a squared is a multiple of 3. Right? So what would end up being is you have to show if a squared is a multiple of 3, then a is a multiple of 3. Which what would be it? Then you show that by contradiction, which is, well, if a is not a multiple of 3, what are numbers that look like not multiples of 3's? It's 3 times something plus 1 or 3 times something plus 2. And then show that the square is either 3 times something plus 1 or 3 times something plus 2. And then you would have shown that. Yes?
How could you prove something more general, like the square root of a prime number is?
Yeah, a square root of prime number will be purely irrational, and it's the same thing we'll talk about. The prime is going to be a factor, which is, okay, if a prime is a factor of a square, therefore the prime must have been a factor of the a. And so you can use the fundamental theorem of arithmetic to show that. In other words, it really comes down to the lemma. This part would change not at all, except for you would have, whatever, 3, 5, 7. What's going to change is your lemma. And once you get your lemma down, which takes a little more work, but not much, you can then show that, oh, the square root of any prime number is irrational. And actually, the square root of anything that's not a perfect square is irrational. And you can get to that point too. But yeah, the heart of it would be the lemma, not the meat of this, the idea that we're doing. Instead of, the common factors and common factor of the prime is where you're going to be at. Yes?
On the test, is the implication lemma, is that going to be part of this proof?
Mm-hmm. I will say prove square root 2 is irrational with any used lemma.
Okay, so we have to do...
You'll do lemma, and then jump straight to the proof by contradiction and finish it. It'll be one page. I'll say prove the square root 2 is irrational and any used lemma. You'll prove the lemma first, and then do the rest of this proof. And I want you to understand it more than anything else. The reason why I think this proof is fundamental is because what are all the techniques that you used? Contradiction, direct, contraposition. You have to understand assumptions. What does it mean to be rational? What does it mean to be not rational? Common factors. This embodies a lot of the techniques that we do, all within one statement. The square root of 2 is irrational. It's also important because people died for it. So everybody looks at the user. Have I said that one? I haven't told you why square root of 2. Okay, the Pythagoreans said everything is rational, right? It's an int over an int. It's nice and clean. You can measure anything. And then they had the following problem, which was this. If you have a 1 by 1 square, how long is the diagonal? And they simply showed is, well, they knew that 1 squared plus 1 squared needs to be the diagonal squared, so that means that 2 needs to be the diagonal squared, so the d needs to be, we'll write it like that, right? Why do we use that symbology? Well, their hope was that, if everything was rational in the world, and that was everything can be measured by take a 1, divide it up into b parts, and then you need a of them. Seems very fundamental, right? Take a 1, how many pieces, and how many of those? And I can measure anything I want. Well, what did we really show? That diagonal cannot be measured like that. It's kind of crazy. Well, what if I use a quadrillion? It will never, I don't care how fine of a gradation you take, it will never line up on a rational ruler, ever. Doesn't matter how fine of a B and how many A's you take, it will never line up. That's what they showed. Well, if your entire world was numerology, right? We can take 1 and divide it into pieces and everything works great. And here's a simple one that says no. Diagonal of a 1 by 1 square? No. Can't do it. And so they said, don't tell anybody. This is our super secret inner circle. Don't tell anyone. And some guy went and told people. and the gods punished him because they went out on a rowboat, and there was a surprising storm that nobody saw, washed him over, and they rowed back, and he didn't make it. Right? They drowned him. It's like, oh, wow, see, the gods punished him for telling these things. So people died for it, so we ought to know the proof. What was us on the other hands? Questions?
Oh, yeah, but I was saying, couldn't you just change your measuring stick so that it wasn't unit of 1 and now it's a unit of 2? And then,
No, it never works. Nothing. Nothing.
no,
If it's an int.
Yeah. But I was saying, you could just change your measurements, how you're measuring this box. Let's say that instead of 1, it was 2, the sides were 2. You just replace
No.
it.
Well, then what you would do is say what? Then what are you doing? You're showing that, what, 4 plus 4 is 8, needs to be d squared, and so now what I'm looking for?
Oh, yeah.
D is the square root of 8,
Oh, yeah, then that's not.
which is actually 4 square roots of 2, so no.
Yeah. So it doesn't work.
Sorry, 2 square roots of 2. Eek.
Yeah.
So, which it still shows back up, which is primes, whatever you pick. If it's not a pure, when you do these problems, it's not going to work. So, all right. Hand in me your attendance. Attendance for next class, you're going to like this one, is 1.7, example 10 in the text. Any guess on what I want you to do for next class?
Square root of 2.
Square root 2. That's what example 10 is. At least write it down once. Hopefully that means that nobody will make the test blank. All right, that's it.